I knew that the previous video wasn't enough. One example isn't enough. So we're continuing. We're going to have two more problems relative to the lesson about solving problems regarding the ideal gas. So we're still going to apply the same formula, PV is equal to nRT, as well as the variables and their corresponding default units. So let's move on to number 2. For number 2, it says that we have to determine the pressure of 0.256 mole of neon gas in a 15.6 liter container at negative 35 degrees Celsius. So I did a few head starts before I started recording. It turns out that this problem is not related to combined gas law. That video is going to be next. There will be at least 3 problems about it, but we have to focus on this one first. So let's enlist our given P, V, N, R, T. So for pressure, we are given nothing. It's what we're trying to find. We have to determine the pressure. 0.256 mole, we know what N is. For volume, we know what it is. It's 15.6 liters. And for temperature, we have negative 35 degrees Celsius. And for Raoult's constant, it's always 0.0821 latom over nk. Now, for our equation, since pressure is missing, so PV is equal to nRT, apply the concept of literal equations, divide both sides with V, it will be nRT over V. This is our equation. Let's go with our solution. So pressure is equal to mole, which is 0.256. By the way, we'll have to set this apart for now. Place it here because we have to convert our temperature. Again, the default units, pressure we don't know, volume, yes, liter is the default unit, mole, yes, latom over nk, yes. So Celsius, we have to convert temperature. T is equal to negative 35 degrees Celsius to Kelvin. Remember our formula earlier. Temperature is equivalent to negative 35 degrees Celsius plus 273. With that, it's basically 273 minus 35, which is 238 Kelvin. Now, with that said, let's move on to our solution. So again, let's continue. P is equal to 0.256 mole. Then our Raoult's constant, which is 0.0821 latom over nk times temperature, which is 238 Kelvin. Let's continue with the denominator, which is volume. So divided by altogether with 15.6 liters. Now, place this expression in the scientific calculator. I hope you have it right now because we're going to need it for the next following problems. So, with them in the calculator, it will be 0.3206531282. Now, for pressure, let's round it off to 5 significant digits or units. So 0.32065 atmosphere. Or you could round it off to 3 significant units, 0.321 atmosphere. Both are correct. You'll just have to ask your science teacher what he or she prefers when you round off your final answer. So both are the same. So for number 3, let's continue with number 3. The pressure of a sample of carbon dioxide in a 1.85 liter container is 0.268 atmosphere at 317 Kelvin. So for our given, Let's enlist again. We know PV and RT. For pressure, we are provided 0.268 atmosphere. For volume, um, we are provided 1.85 liters. For number of moles, that's what we're trying to find. Determine the number of moles of gas in the sample. For Raoult's constant, as always, it's 0.0821 latom over Nk. For temperature, we have 317 Kelvin. So for the first time, compared to the previous problems earlier, we don't have to convert anything. All of these values are in their corresponding default units: atmosphere, liter, latom over Nk as always, and Kelvin. So we're trying to find mole. Let's formulate our equation now. So PV is equal to nRT. Let's start from that. What we're trying to find is mole. So divide both sides with RT, so we get this kind of equation. So for solution, let's just move it here to make the space a little more prettier, less dense. So mole is equal to pressure, which is 0.268 atmosphere, times the volume, which is 1.85 liters. Altogether divided by our Roth's constant, which is 0.0821 latom over Nk, divided by, times our temperature, which is 317 Kelvin. So place all of this in the scientific calculator, and we will have, please pay attention, this is going to be really tricky. Please don't confuse the numbers. 0.01905040018. Make it less confusing. Round it off to 5 significant units. 0.01905. Then place the unit, of course. That will be a deduction if you fail to place a unit, because it's really crucial. Placing a unit is very crucial, as a great teacher once said. He stated that without a unit, it's going to be misleading, and your experiment may lead to disaster, just because you failed to place a unit. For example, if you place 24, what 24? 24 centimeter? 24 meter? Well, if you mislead the idea of the true measurement, you're going to result to unsatisfactory results. It's something like that my teacher said. So that's it for this video. It's just a supplementary video about the previous one, about chapter 1. So please expect chapter 2 after this. Thank you for watching.